All right, thanks. So, hey guys, good to see you all here. I hope you're excited, as much excited as I am, because we're going to have a hell of an evening. We're going to build a synthesizer in JavaScript. So that's going to be about music. And as always, I start my presentations with a nice picture that's kind of relevant to what we're talking about. So first, a question to the audience. What kind of musical instrument do you think this is? I mentioned someone saying a harp. That's quite close, but not correct. Any other thoughts?
Some kind of guitar?
Almost, almost. Well, let me tell you. It's actually called a concert zither. This is a kind of instrument I play myself too, and it's actually a hybrid between a harp and a guitar. So you were both half correct. So you have to share a beer. So no, but this is it's an instrument which is traditionally played in Bavaria and Austria, and it's a very nice thing. A very uncommon instrument, very cool sound, and it's very versatile. But it has actually nothing to do with synthesizers. So let's continue on. A little bit about me. So my name is Emil Loer. I'm a developer for Groningen, and I do mostly these days indie Mac and iOS development for myself, my own apps, but also for other companies. And I do consulting and a little bit of developer training. So if you have interest in any of those services, feel free to contact me afterwards. But this is not going to be a sales talk, so whatever. You might also know me from my other company, and I'm CTO of Bartune. We make music players in bars and restaurants and all that stuff. So, who here has ever heard of the Roland TB303?
Oh yeah.
The response is exactly what I would like to hear, because this is actually, if you want to name one musical instrument, this one would be my favorite. And this is the Roland TB303. It's a baseline synthesizer made by Roland in the 80s, and it's iconic because it's used in a lot of both old and new electronic music. It's a very simple device. It basically has 16 notes that you can program, and these notes are played in succession, and then they're looped over and played again. And there are a bunch of knobs, and you can twiddle with them to change the sound, to make it a bit softer, a bit sharper, to change the waveform. You can put accents on notes. You can let notes slide from one note to another. All kinds of things. And also, of course, you can change the speed and the volume and all these things. So why am I showing you this picture? That's because we're going to build one today. Or actually, I've built one already, and I'm going to show you how I did it. Because it's still quite a lot of work, and we don't have that much time. So that's how we're going to roll. So what you see here, you have a bunch of knobs to change all these parameters. You have the dials as well. There's some output, of course, and all of these things are the components that are part of the synthesizer. And we will have to build those in JavaScript as well. So in order to do that, we have a couple of libraries at our disposal. So we're going to talk about those. And of course, there's also the user interface part and also the communication between these things, like how are these components connected to each other. That's also a very interesting area to talk about. So we're going to talk first about browser-based audio. And this starts with the days of Christmas past. Because back in the day, when browsers first arrived, it was very hard to do audio in the browser. But at some point, there were some guys, and they made a couple of technologies that made it possible. And one of them was Java applets, and the other one was Flash. And while this is not, people don't consider this to be native or whatever, but these technologies did enable users to write code that could create sound and output sound, or maybe record sound, or whatever you want with it. But they're not part of the browser themselves. They're third-party software that you have to connect to, and that's annoying. And of course, this brings all kinds of problems too. So there had to be a better way, and there was, because Mozilla, or some guys at Mozilla, they thought the same thing, and they thought like, oh yeah, well, we can just create an API for this that can be accessed from JavaScript. They called it the Audio Data API. And this API basically had functions that could say like, OK, I want to set up a stream of audio that generates audio or reads audio or does something in the middle of an audio stream, so changing the data, for example, or analyzing it. And they did this using a set of callbacks. So you set up your audio stream and you give a function to the API. The function gets called whenever there's new data. But there were a lot of downsides to this. I'm not going into the details of this because Mozilla itself said, okay guys, we made a huge mistake. This API sucks. We don't want you to use it anymore. So instead, we're going to use the Web Audio API, which is sort of the successor, but also not, because they were partially designed in parallel. I keep getting email, by the way, so I hope you're not distracted by that. Yeah, so this is the Web Audio API, and this is the one we're going to use. I'm going to show you how it works, and also a little bit about its history and how we're going to use it in our synthesizer. So today, that's the most used or the best used choice. It's also widely supported. I'll get to that in a few moments. So whenever you want to do audio, forget all the other things. Use the Web Audio API, unless you target Microsoft devices, but who does anyway? So the Web Audio API, it's a W3C standard, which is good. It's currently in a working draft state, so that means it's not officially a recommendation for browser vendors to adopt, which is bad. But there are a lot of working implementations already, and the last updated version of the standards by W3C was in October 2013. But the standard existed already quite a time before that, and actually there have been several revisions already. I believe the first one was in 2011, so that's quite a while ago already. But it started in June 2010. And there was a guy called Chris Rogers, and he also thought about audio and doing audio in the browser, and he was fed up with the existing solutions. And he also said, there's got to be a better way. But his way was different from the Mozilla guys, because he said, I want to approach the W3C, and I want to make sure that this becomes actually an official standard that other browser vendors can adopt to. Whereas compared to the Audio Data API, that was just some hack that some happy developer created just to solve his own problem. Now, these guys at Google, they wanted audio support in the browser to become available everywhere. So that's how the Web Audio API project got started. And it's still heavily under development, because last update of the standard, the GitHub version of the standard, was actually yesterday. So there's continuous improvement. But this also has a downside, of course, and that means that things will change. So you have to be careful about what you're going to use, and carefully look into the documentation and on the support websites to see which parts of the Web Audio API are currently supported by the platforms that I want to target. And these are the platforms that are supported. We've got Firefox and Chrome, and they have long-time support for the Web Audio API already for many versions. So if you want to use it, you're basically safe on these platforms, assuming you don't use the bleeding edge new parts that are in the Audio API. I will mention them later. Then there's Safari and Mobile Safari. They work too, so that means you can use the Web Audio API on iOS. Or on Mac, starting with OS X Lion and newer, so that's good too. Opera has support for it for a few versions, not that many, but who's using Opera anyway? And the most important thing I did want to mention about support is there's no support for Internet Explorer at all, and it doesn't look like Internet Explorer is going to support it soon. So yeah, that sucks. But that said, you can still use one of the fallbacks. For example, I built a music player in the browser once before for my bar-tune company, and over there we use the Web Audio API for rendering audio, but we have a Flash fallback for using for our customers that have Internet Explorer. So, and it works pretty well as long as you make an API that's roughly compatible to the Web Audio API, because you don't want to do any double work. But yeah, but apart from that, support is pretty good. So how are we going to use this? Well, everything in the Web Audio API is based around one kind of managing object, and that's called the audio context. Now, in order to start using the Web Audio API, you have to create a context, which is just as easy as this. there are a bunch of properties that you can modify to change the parameters of the sound that you're dealing with. For example, you can change the sampling rate, you can change the bit rate, you can change buffer sizes, so that means how responsive the audio will be to real-time generated audio, and all kinds of things. But the audio context has one more property which it manages, and that is the audio graph. And I will explain this in the next few slides. But basically, the audio context is the barrier between your code and the audio device. And behind the scenes in this thing, there's a lot of magic to make it happen. So, but luckily, the API is simple enough that we don't have to deal with most of that stuff. We can just create our audio graph. And for those who don't know, the audio graph is a directed graph, and it's acyclic, so that means no loops. Audio flows from a source to a destination. The destination is given by you, by the audio context. And the destination basically means your sound card. So whenever you shove some data into the destination, it gets output, and you can hear it. Data has to come from a source, and what kind of source that is, well, that's up to you. There are a couple available, and you can create your own sources. Of course, the setup can be a bit more complicated, because if you're doing stereo, then there are multiple destinations, because there's a destination for each channel, so left and right. And if you have a sound card with many outputs, there will be even more destinations. So you can make your own branch of this graph that goes to a specific destination. And there are also nodes in this graph that do this splitting automatically. So you don't have to duplicate anything if you don't need to. Now, one thing that's new compared to the previous slide is that we have here also some processor nodes. These are basically nodes that take an input and have an output, and they either do something with the sound in terms of modifying it, or they just analyze it. For example, if you want to take a look at the spectrum of an audio and you want to display that on screen or anything. It's just something that takes the data, outputs the data, and if it wants to, changes the data. And of course, there's still some generator or source node, if you want to call it that way, that creates this data. And one thing that's interesting here is that a node can output to many nodes at the same time, and there's no limit to the amount that it can do. Well, the only limit is, of course, your computing capability of your computer. But despite that, it's limitless. So there are a lot of possibilities to explore. Now, here are the nodes. I split these over 3 slides because there are a lot, but I try to categorize them. So on the first slide here, we have the sources and the destination nodes. Well, there's actually only one destination, which is the destination node, and it's given. You can't create it yourself, and you don't need to, because you can just put something in there and you have audio output. I must say that there are some other nodes which I didn't mention in these slides for outputting data to a stream, but these are not in the official W3C standard yet, so don't use them yet. There are a bunch of sources here. The media stream is for the microphone, the audio buffer is for an audio file, and the media element audio source is for an HTML5 audio element. So these are ways to get audio from something. So these you would use as the beginning, as the most left side of your audio graph. Then there are 2 others, which are the audio worker node and the script processor node, which basically do the same. And the nice thing about these nodes is they can be anywhere except as destinations. So, and what these do is you give these nodes a bunch of JavaScript, and the audio API calls these JavaScript functions whenever either it wants to generate some audio or when it wants you to process some audio. So these are basically your own custom nodes implemented in JavaScript. And the script processor node just calls a JavaScript function, and the audio worker node does the same, but in a web worker. So that's a more concurrent approach to doing this. The audio worker node is not widely supported yet, So we're going to use the script processor node today. However, I must say that when it is supported, it is a more superior approach. So you should definitely use that instead. And in fact, in the latest version on GitHub of the Web Audio API spec, you can see that the script processor node is actually deprecated. So things are moving quite fast. But the browsers haven't caught up with this yet, so we'll have to wait a little while before we can actually make this change. So here are a bunch of nodes that can be in between an audio stream. So we've got the gain node, which changes the volume, the panner, which changes left and right. So this one takes 2 and outputs 2 nodes. It's a bit different. The channel splitter splits it into multiple destinations. Merger merges them together. So these are like mixers, if you will. The dynamics compressor also does something with volume based on the volume of the signal that's going in. So you can respond with volume changes based on, for example, if someone is speaking or not. It's very useful. And the analyzer node is kind of self-explanatory. It analyzes the signal, and you can get the spectrum and all these things out of it. So if you want to do cool music visualizations, that bottom one is the way to go. Then there are some more advanced nodes. And these kind of are in the domain of synthesizers already. We're going to use techniques used by this node, but but we are not going to use the nodes actually, because we are going to work on a lower level. So we're partially implementing these actually in code. However, these are quite interesting because these nodes are actually more advanced transformations of audio. So we have a biquad filter node, which is like an equalizer knob on your audio. You can change the relative strength of certain frequencies in a node. I won't explain in depth how this works because it's quite mathematically involved, but it's a very important component in synthesizers, I will say that. The wave shaper is basically your distortion. So if you want to distort audio, you can shape these waves to a different shape, basically. The oscillator is a tone generator. We're going to design one ourselves. And the convolver is an effect that you use if you want to do like reverberation, these kinds of effects. The convolver node is also quite new. It's not really stable yet, so we can't really use it yet. So synthesizer components. Well, a synthesizer by itself is basically it's kind of like, if you express it in mathematics, it's a function that over time produces an audio signal, and this audio signal is just a bunch of floating point numbers. So that's basically what we're going to do. We're going to build a function that has some state, and if you call that function over and over again, that's basically the T that we're doing. If you do that, then you get these numbers, which are audio signals, and we're going to output them to the sound card. Now, of course, writing such a simple function can only give you a simple tone. So we're actually going to define a bunch of additional components that we're going to include in this thing. And the first one is the oscillator. Now, there's a lot of math involved in this, and I will say that I'm not going to explain everything of it, because there's just a lot of it, especially if you're going in filter theory and stuff. So I'll cover just the bare basics here, and if you want to explore this subject more, well, feel free to ask me some questions afterwards. But basically what we're doing here is, this is the slide which defines the oscillator. The oscillator is the tone generator, so that's the most fundamental part in our synthesizer. So it's basically a function given us a bunch of parameters. It outputs a waveform, and this waveform is the audible signal. It takes as input a bunch of parameters. For example, a pitch, which is the P. It takes a sampling rate, which means how many numbers are we going to generate per second. This is so we can map the pitch, which is an abstract value, to actually a frequency. In order to compute this, we're using something which is called the Fourier series, which basically means we're not just going to generate a function that, using an if statement, for example, generates a square wave if the period is less than a half, then it's high, and otherwise it's low. No, we're going to use something called the Fourier series to make it free of any defects in the sound. Now, I'm not going to explain this because it's very complicated, but generally it means that once we start processing this further, we get a signal without distortions. Wikipedia has a very good explanation of this process, so look that up if you're interested in that. But that's the oscillator part. That's the first part. And then we're going to change the sound, because an oscillator by itself sounds very boring. It's just one note. There's no change in it. And when you look at a musical instrument, for example, take a guitar. Like you have strings. You strum a string. What happens? The string doesn't vibrate endlessly. Something changes. And this is also how we can distinguish this sound from other sounds. The change in the sound is very important. So what happens with a guitar? Well, first of all, once you strum it, the sound changes in strength. So once the sound gets older, if you wish to call it like that, then it gets quieter. But also it gets softer. And the softer part is what we call in synthesizer theory a filter. So a filter is basically something that takes an audio signal and over time changes the content of the frequencies in this sound. So you could, for example, say like, okay, I start this sound with all rich tones in there, all kinds of overtones. And over time, I want all these overtones to fade away and only one fundamental frequency remaining. This is something you can do. You can also do the opposite. You start with one tone, you add new tones and all that stuff. And this is something which is very interesting in that you can model the actual sound using these filters. Now it's a bit abstract what I'm telling you here. I'm going to show you a demo later that in sound describes what I tell here, and then things hopefully become a lot clearer. So next to that, there's another part which is kind of important, which are called modulators. And modulators are basically additional variables that you put into these big equations that change parameters over time. So as I said, the guitar, it changes volume over time. This volume changing is a modulator. And there are all kinds of modulators. Some follow a shape, some are randomized for certain effects, for example. Some are just constant, or some are even tied to like buttons or knobs. We've implemented a couple of them, so I'll show you how that works. But they're very important because if you have the ability to change the sound over time, you have the ability to make it interesting. And next to that, we have some effects, because if you have just the music, well, at some point, if you play the same piece over and over, it gets repetitive too. So we want to actually enrich in the sound with some effects. And one of these things is distortion, which we're going to see, and an echo, which is also something we're going to see. But there are other things like reverb or chorus or flanger. You know, all these guitar effects that you have as a guitar player, those are kind of things you can implement in software too. But we're not going to cover this in very much depth, because it's more of an advanced topic. So we're going to model the TB303 because, as I said, we want to create this thing. So we have to understand how the TB303 actually works. There's a lot of literature about this, and it's also a little bit of a hobby of mine to explore these things. So I did the homework already, and I came up with this big graph. Now, unfortunately, it's a bit hard to read, but I don't really want you to read it anyway. I just want you to know that it's kind of complicated. There's a lot of dependencies here. But what's most important is that each of these things is either an oscillator or a filter or an effect. And we chain a lot of these things together to get the sound that we want. So in the end, for example, we have here our distortion, we have our delay. Here in the beginner, we have our oscillator. We have a bunch of filters that changes it. The way these are set up are what defines my synthesizer as having the unique sound that I want it to have. One thing that's also interesting to see in this graph is there are a bunch of parameters. These are the modulators that go into these filters. So for example, here we have something which is called diode ladder filter, which is the central part of the TB303 sound. And it can be changed using a bunch of these knobs. And this allows you to get these real cool bass lines with this instrument. So we're going to build this thing. And because this is a very complex object, we can't really use the stock web audio API components for this. It would be cool if we could, but the web audio API components do not allow you to change parameters during the audio stream, only after a part of the stream has been rendered, and then the next chunk and the next chunk and the next chunk. So changing sounds over time is very hard. So what we're going to do is we're going to create this script processor node that manually implements these things. By the way, I will say, I forgot to mention this already, but I will publish the source code for this. It's not that much code that it's going to result into. It's only the entire synthesizer core is 500 lines of JavaScript. So it's quite compact, and you can clearly see all these components there back because I've documented this. So if you're interested afterwards, I'll place it online, and you can just have a look at how I did this. But now that we have our abstract representation of this synthesizer, and we know what kind of components it has and what it has to do, we actually have to design a piece of software for this. And this starts all the way back because at some point when I was at university, some person that I knew, he approached me and he said like, hey, you should do a TB303 implementation because you do synthesizer and stuff. And oh yeah, you also should do it in 100 lines of C code because you like C. I was like, okay. So I built this thing called tiny303.c. It's an open source 303 synthesizer, 100 lines of C code, no optimizations or whatever. It just generates an audio file when you run it, and it produces some music. So that's very cool. But this is something I created like 5 or 6 years ago, and I decided to use it as a basis because it has all the research already in there. So the architecture was going to be like this, but then JavaScript and real time. And it turned out I didn't have to change a lot of things, so that was nice. Now the next question is, am I going to use CoffeeScript or am I going to use JavaScript? Because I hate JavaScript. And oh my, what am I doing here? I'm at a JavaScript meetup, so I don't like JavaScript. Well, it turns out I do like CoffeeScript a bit more. But there's a problem with CoffeeScript, and that is CoffeeScript is a preprocessor for JavaScript, meaning that you don't have very good control over the performance characteristics of your code. And this is something, when you're doing audio, it's very important. The end of the presentation will be about performance considerations building with that come to mind with synthesizers. I'm going to give you a few tips, but I decided to build the thing in JavaScript because I saw that some things in CoffeeScript, especially related to loops, introduced a lot of unnecessary code that might make the code clearer, but also make it slower. So the synth itself is in JavaScript. But that said, I hate JavaScript, so I want to write my user interface code in CoffeeScript. So I did that. So there's a hybrid between these two. I used Ember for the controls because a synthesizer is not really cool if you can't put notes into it and hit the play button and twiddle with the knobs and stuff. So yeah, I made a small Ember implementation of that. It's I don't know, it's about 400 lines of code or something. Very small. It was actually my first Ember project, and came to the conclusion that I actually like it. So yeah, that's nice. So let's give it a demo. Let's see what this thing actually looks like. So there, this is JS303. This is the JavaScript synthesizer that I built for this. Let's start with the part below, because this is the music that we're going to play. Now, as you saw in the picture of the TB303, there was like a piano keyboard, and there were not that many buttons. So it took you a lot of steps to actually program in the notes. And I figured like it's much easier if you just project all these notes into a grid. So that's what we did here. I used MIDI numbers for the notes just because I was too lazy and too short of time to actually put note names in there. But so what happens is you have a note here. You have another one, and so forth, and these are just notes at different pitches. Now, each 4 groups of notes, I make a little highlight to make it easier to see where you are. Then here's the number of steps that we're dealing with, so you can easily count them. And here below are a bunch of flags. These are also important for the TB303 specific sound, because in the TB303 you have something which is called the gate, which means is the note turned on or is it turned off? So that's this flag. Then there's the slide, which means should the note slide to the next note instead of just playing the next note together. There's an accent, so make a note a little bit louder and add a bit of extra effect to it. And there are octave up and octave down, which basically means play this note a lot higher or a lot lower. Now, on the right, we have a bunch of buttons to randomize and clear the patterns, which is kind of cool, and you can start and stop them. And on the top, this is where the this is where the magic happens. We have 2 rows of knobs, and the top one, these are actually the knobs that are on the TB303, including this button here to choose the waveform. And I added 2 effects just to make it a bit more interesting. I added a foldback distortion and a delay. So a foldback distortion basically makes the sound really loud. At some point the sound gets too loud. Your sound card can support it. And what the foldback distortion does is it flips the top and the bottom part of the waveforms to make a lot of interesting extra sounds in there. And these are configurable, so you can change how much the sound is increased in volume and also where the foldback point happens, so how much of that gets fold back. Then there's the delay, so we say we have a delay of 3 notes, and we can say that a part of the signal gets put into the delay, so you can say like, okay, I want half of the signal I want to hear back as an echo. In this case, we don't want anything because I want to let you hear the dry signal first. And the delay has a feedback, so if you feed back some of the signal into the delay again, you get an endlessly going on echo, which is kind of cool. So what I'm going to do is I'm going to play this synthesizer. I'm going to twiddle with the knob. So we'll get some music, and I'm going to show you what all these buttons do. And yeah, well, let's see what happens. Let's see what a browser can do. So let's go down first. We'll see. This is the sound what you get. I hope everybody can hear it. It's a bit soft, but it will get brighter over time. So you see, if you hear correctly, you see these accents that get played. So they're very soft. So bum 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 bum. Then there's a high note, which is over here, and it slides back down. So it gets like, woo. That's what it does. Yeah, I'm not the best in generating these synth sounds with my voice, but that's why I created this thing. So yeah, and then these notes are a bit higher, so you can clearly hear these things. Now, let's change some of the parameters. Well, here's of course the speed. That's self-explanatory. I don't need to explain this. But the cutoff frequency is very interesting. So what we're going to do is one of these filters chops off all the high frequencies, and all the lower frequencies are let through. Now, if I change this button, the amount of high frequencies that get chopped off will change. So if I put it higher, then more low frequencies are let through and less high frequencies. And if I put it lower, then the opposite way around. So what happens is, if I lower it, then the sound gets more dull. If I increase it, the sound gets more rich. So let's see what happens. You can already hear some electronic music that sounds familiar, right? I mean, a lot of simple techno music uses just this button, and people go freaking on this button, and yeah, just add a beat and you've got a hit song. That's how it works. So download my code and be a musician and publish your own song. All right, so resonance is something which changes the filter just a little bit. It adds a bit of a spike to it, creates a bit more of a snappy sound. So if I put it up, you don't hear much of a change. But the change really happens when I put the cutoff high. You see that it gets a lot snappier. Now, nth-mod is a very interesting knob, because what this one does, it actually adds a bunch of values to these buttons over time. So whenever a new note gets triggered, these two buttons or two knobs actually get a bit of a bump. So they bounce around all the time, and it makes the sound yet even more interesting. So let's add some of that. You can hear now that the beginning of the sound is very rich in frequencies, and when the note progresses, it gets a bit softer again. Now the decay is the amount of decay over time that the sound has. It's kind of like it's kind of like, you know, a radioactive signal, like or a radioactive thing you have. Over time, you get less and less of it, and this is the same with the sound, so it fades out. So now we want it to fade out in 0.1 second. We can change it to 1 second. Our sound gets longer. So that's that. Then we can change the accent. Now we just hear the accents because they get amplified a lot. We get a different sound. So let's add some delay because and now is the interesting part. If I stop it, the delay keeps on going. So and this is what makes the feedback button fun, because if I play it again and I put the feedback high, I stop, then you see that each pulse means 0.96 times that original signal. So you see that it decays out. It takes a long time to fade out.
Now you should put the next one.
Yeah. And last but not least, the distortion. So the distortion really corrupts the sound. So it gets louder, and then we start to change it. And a bit lower. Oh, this is exciting movie music. So, yeah, that's my demo. I hope you liked it. All right, so what you saw here was this synth was real time, and it responded immediately to the changes that I made. There was no delay, there was no stuttering or whatever. How is that possible? Because this is JavaScript. This is the world's slowest language, right? So, yeah. We have to make it fast. But first of all, we have to ask the question, why do we have to make it fast? Because computers are fast enough anyway, right? Well, it turns out that the browser is not constantly just rendering audio. It's also doing other things. For example, you have different tabs, and they might check your email, or you might have a more complicated web service that does network communication while you're doing this audio rendering. Or maybe you have a Facebook button that secretly does all kinds of stuff that you have no control of. Who knows? You want to make sure that your code isn't the fault. And this is especially important because when you're using the Web Audio API, you get a callback. And this callback has to provide audio. If you don't produce enough audio on time, you get a stutter in the audio. And this is something you never should have, because that's bad user experience, right? And that's something we all know about as web developers, right? So and with audio, it's just the same thing. So how do we do this? Well, we have to make use of the JIT, the just-in-time compiler that is inside our JavaScript interpreter. So the JIT basically compiles our JavaScript code that is much used into machine code. And it does a pretty good job at this. Actually, it does a hell of a good job at this. But the JIT isn't like a Mr. Know-it-all. I mean, the JIT doesn't really know what you're using the code for and all these kind of things. So we have to help the JIT a little bit and massage the code a little bit to make sure that it can convert this code into the most optimal CPU instructions. And there are a bunch of tips that I can give you. And you can use these in your own code too. You don't have to be building synthesizers. If you're doing WebGL or like browser-based games that also suffer a lot from computational performance overhead, you can really use these tricks too. The first one is whenever you're using arrays and you only store a single type in it. So for example, you have an array of floating point numbers, or you have an array of integers, or an array of characters, or whatever. Use WebGL typed arrays. Now WebGL is the OpenGL standard for making, it's like the web standard for making OpenGL based games and all that stuff, but it also adds a bunch of extra classes which are really useful. And one of them is a typed array, which basically is like a JavaScript array, but it only has one type. And the implementation in the browser is very efficient, I should say. And if the JIT knows that you're using typed arrays, then it will do all kinds of optimizations, because it doesn't have to check the type of what's in there and all that stuff. So that means that the JIT can reason better about the code that you're producing. And especially here, since we're just producing floating point numbers all the time, we know that every single thing that we put into this audio buffer is the same thing. So it really makes sense to use something like this. Then this is also something, it's kind of interesting. The dot, it's your enemy. From now on, the dot is all of your enemy. Because the dot basically forces the JIT to take a step back and to take a look at the code and think like, oh, hey, but you're doing object lookups. But this is an object lookup, so the object might change somewhere else, especially if you're using web workers too and all these kind of things. Things start to happen in parallel, and timers, who knows what. So whenever there's a dot, then the JIT will actually stop for a moment, and it will implement an object lookup there. And the object lookup is something which is slow, actually, and especially if you're doing a lot of these things in a small function like the synthesizer that we've seen, then things might get a lot of overhead. I actually did a profile on my code, and I saw that just object lookups was about 40%. So I eliminated most of them by making sure that everything lives, every bit of state just lives as a variable inside of a function, and it doesn't. We don't use object lookups, and also if we do multiple things with an object, then we cache the object lookup into a variable. So what we're basically doing is, like, say we have some object and we have some property on it. Let's call it foo.bar. Then if we want to do 3 things with bar, like we say we want to add 1 to bar and 2 to bar and 3 to bar, then what we do is we don't say foo.bar plus is 1 and plus is 2 and plus is 3. No, we say some variable, let's call it, I don't know, my bar, is foo.bar, and then we change these things, and then we put it back. So that way we saved one lookup. And if you're doing more and more complicated computations, you save a lot more lookups. And this actually helps make the synth really fast. But of course, it might be overkill for a lot of applications. For example, if you're doing database stuff, yeah, you're not interested in this, of course. But for example, WebGL stuff, I've really seen people use this trick too, and see a lot of benefits here. So another thing is we can pre-compute a lot of data. For example, I showed you this slide with the big Fourier series equation, and that was ON squared. So that's not an efficient computation. However, a lot of these things can be factored out and put into a lookup table. So let's do that. So what I did is on page load, we get a lot of lookup data that gets pre-computed, and then we just have a table lookup. That's a lot more efficient. However, it turned out that pre-computing was also quite slow. So what I did is I preloaded. So I took this data. I actually ran my generator in Node.js, saved it into pixel data of a PNG image. Because what happens if you put this lookup table data into PNG, you get lossless compression. So you can download that PNG. You can extract the pixels again using Canvas and put it into a typed array. And then you have custom data that gets losslessly compressed, and you can reuse it again in its original form. So that's a really cool trick.
Was it a sign table, or?
Yeah, it was a sum of signs, basically. So yeah, it's basically what we're doing is for each pitch that we want to support, for each node value, we have a sum of signs into one sign, one sample table combined. Because we're selecting waveforms based on the pitch to make sure that we don't get any unwanted overtones above the maximum supported frequency of our audio device. And the next thing is what we can also do is we can cheat precision. Now, what I mean with this is we don't say something like, okay, we've got floating point numbers and we change it to fixed point or whatever. No, that's not necessary. But what we are doing is we are, per sample, generating a lot of data. Some of this stuff is based on intermediate computations. Like some computations have maybe a shared step or something. And the question is, do we need to actually recompute that for each sample that we're computing? Or can we get away with just, I don't know, computing it every 16 or 64 samples or whatever? And it turns out that in some cases we could. So for some of the data that really that was quite involved, for example, using a power computation, so like a power of 2 or something, I actually used this trick, and it saved a lot of cycles. And yeah, the nice thing is that we don't actually notice a difference because it was we were saving a temporary value in 64 samples, but if you compute the number of seconds of time that actually is, it's just not noticeable. So you wouldn't hear it. So we could get away with these things. So that's also another trick that I did. So some final thoughts. This was my talk about doing synthesizers in JavaScript. I hope that everybody saw something new, or at least learned about a completely new discipline in the world of JavaScript programming. I'm not going to ask you to write your own synthesizers because it's very damn involved and it requires a lot of expertise in like this signal processing stuff. But I do hope that you had a good time watching my presentation. I will make the source code available, but there is still one bug that I had to fix and I didn't have time for it because I built it last weekend. So once I do that, I'm going to release the code, I'm going to put it on my GitHub, and I'm going to make an announcement at the meetup page with the URL and stuff. So you can try it at home. This thing should work in no, yeah, a lot of browsers, so just toy around with it, create your own sounds, and if you create some hit single using my code, I would like to be noticed. So thanks. So any questions? Yeah, on the back.
What does the generated PNG look like?
The generator in PNG.
No, the generated PNG.
Oh, you want to see it? Yeah, I can show you. Let me see now. It should be over here. Let me see where it was. I think here, yes. There it is. But this is actually kind of interesting because you can actually see what I'm doing here and how this Fourier series works. Because what happens here is we have two waveforms here. We have a sawtooth and we have a square wave. Let's take a look at the square wave because it's a bit more simple. You basically see that on the top line we only have one overtone. So it's very simple, this thing. But as you go more down, you see a lot of change in the signal. You see a lot of wobbling and stuff. So that means that the signal gets more complex with these things. So there are a lot of overtones in these lower ones and not in the highest ones. So that's why we actually generate these things, because we want samples with different amounts of overtones. And something else which I can mention now that we're seeing this is you see some empty lines, because that's what, for some note values, I decided the amount of overtones was equal to the one that was below. So what I did is I didn't recompute this thing. I just put in zeros and made a note somewhere in the loader that this value can be reused. And what happens now is that these zeros are actually very well compressed because of something which is called run length encoding in the PNG file. And I don't need this data, but it doesn't cause any overhead. So it allowed me for a very efficient lookup. And also keeping this a power of 2, which compresses well too again. So
Nice.
a little segue there. So any other questions? Yes?
JavaScript is slow, but isn't that just the DOM code that's slow? And not...
Well, I have to tell you that I am a
quite
C
fast.
programmer.
Yeah, okay. But then, because I compared it a while ago with just Fibonacci, and then JavaScript was only, I think, 10 times slower.
Yeah, of course. But seriously, when are you going to write Fibonacci algorithms? You never do, right? So this comparison is completely useless.
Yeah.
But I mean, write some more complicated code, and then you really see some parts which make JavaScript fast, some which make them slow. For example, these object lookups is what makes JavaScript slow. And if you're doing a lot of computations, it's definitely not the fastest language. I will say, though, that it gets better over time, and we've gone a long way already, especially the 8 project, and Mozilla's JavaScript compiler nowadays is also very fast. So we're getting there, and there are actually, especially if you're into computer science, there are a lot of interesting research topics that people are dealing with here. So you could check that out if you're more interested in the performance characteristics of browsers in general. But what you said is true. DOM is slow, definitely. But I'm not dealing with the DOM too much, happily, luckily. So it wasn't really something I had to deal with here.
Yeah, a while ago I was working on a demo in the browser, and I was interested in the spectrum.
Yeah.
So Google had this analyzer node,
Yeah.
but Mozilla didn't adapt it yet. So I tried implementing it myself, and I couldn't get it right. But both browsers are now using the same implementation. Is that correct?
No, they use the same standard. So
Okay.
the standard just defines like, okay, this is the API. These classes is what we got, and we've got these functions in these classes, and they have to do this behavior. But the way they do it, these browsers, that's completely different.
Mm-hmm.
What you, for example, could see is that the difference in audio frameworks that are used behind the scenes is completely different on different platforms too. Because, for example, on Linux, there's multiple ways of doing audio output to your audio device. And at some time, Chrome and Firefox were using different implementations there. And they discovered actually that one of the audio implementations for their framework actually had bugs. I don't know the exact details here, but you see a lot of changes there, and that's why it's important to test on both platforms, of course. And also one thing that's interesting is, and that's exactly what you said, the analyzer node was not implemented on a specific version of your browser that you were using. And this is something you see with some other components too. But what you also see, this was especially in the early days of the Web Audio API, but it's still a problem, is that you've got Windows, you've got Mac, you've got Linux, but the implementations of all these Web Audio APIs, even on the same browser, are not identical. They use different things behind the scenes, so things might or might not work, or might not be implemented. So test it on the platforms that you're using it for. Okay. More questions?
You said the audio graph was acyclic?
Yes.
How did you implement the repeating the delayed repeat?
Well, that's actually audio data stored in a buffer. So it's not part of the graph. It's something you take out of the graph, store it, and then use it again.
Okay, so it's basically a finite repeat that you do. So if you set the
it's basically
decay
a circular buffer with a read pointer that is somewhat behind. Yeah,
that's clever.
But this is something interesting that I can tell a bit more about, because the actual synthesizer function, that entire thing is one audio node. So everything with feedback and all that stuff that happens in there is just JavaScript. And there I can do what I want, of course. If you need the complex behavior, you can just code it yourself.
Okay.
Yeah, I don't want to put you under any pressure to show your code earlier than like when you want to open source it, but could you highlight some of the optimizations you did apart from the local storage of the dots?
Well, I didn't say it because I thought there was no time, but I'm so thrilled to do this actually. So
all yours.
all right. This is the beast. Let's see. I will make the font a bit bigger because I don't think anybody can read this. Is this fine? Or do you need it bigger? Bigger, like this? Yeah, excuse me for using small fonts. I've got good eyes, as you can see with my glasses. All right. So I'll walk you through, and I'll do it quite quickly because there's a lot involved. I won't explain every function, but basically what we have here is a bunch of functions that generate filter coefficients. They do a lot of trigonometry and stuff just to initialize a bunch of stuff. These are like constructors, and they return just arrays, because who needs objects for this anyway? Just an array is fast enough. So that's an optimization here. Let's see, what else have I got? Well, you see some more of this. Here is a polyfill for a hyperbolic sine, because that's not supported under Firefox. So I had to make that myself if it wasn't present. This is actually some code from Mozilla. Oh no, I was mistaken. The Chrome 38 has it, and below it hasn't. So, but anyway, that's that. Here's another filter that uses this hyperbolic sign. Once again, we output a bunch of stuff. This is the state. This is actually the object. So you see some zeros in the beginning, and these are actually the state of the filter, and these change over time. But I didn't want to use any object lookups. I just wanted to use array lookups. Now, arrays and objects are basically the same in JavaScript, but actually they're not, because if you're just using numeric indexes, then the JIT will do an optimization which can deal with very quick lookups. So that's a performance gain that you get there. It's small, but it's still there. Let's see, blah, blah, blah. OK, this is the actual synth. I implemented this entire thing as a closure, because why not? It makes things fast. There's a callback for when the step changes. This is to update the display. These patterns are coming from the Ember implementation, which I will show soon. There's a whole lot of variables and state. Here's a float array for the delay buffer that we had a question about. So it's basically just an array of 2 seconds. And we rotate this thing around using a bunch of pointers. There's some legacy stuff here that I need to remove. Here are some setters for various variables. For example, the tempo has a bunch of derived variables from this. If you're from the Ember build, it's computed properties, but those are slower than this, so I compute it like this. A lot of stuff here. I pre-computed these numbers because these were complicated exponential functions and stuff, and this function is actually called very often. So I just put these numbers in there. There are a bunch of others there too. These are the filter banks. They're just these arrays that we've seen in the beginning of the file with certain frequencies attached to them. Here's another filter with some state. This one doesn't need any pre-computed stuff. So this is basically the reset function, which is called each time you start the sound. Then the render function. This is the most important part, and it's actually built in 2 parts. The first part is the sequencer. So that's the stuff that has to happen each time you change a note. So it has to compute like, OK, what's the frequency of this note? Are we going to slide it? Are we going to turn it on or off? Or is it an accented note and all that stuff? So that happens here. So we advance the sample position, and if it's longer than the length of a total step, then we go to the next step. We change patterns if we need to, so you can have multiple of these pieces of music that you saw. Then we compute the pitch. We do some computation to set the decay envelope, so how much of the sound changes over time. The sliding. There's still some to-dos for more improvements, because you always get ideas when you're working on this. You know this, right? OK, so here is another trick. This is here we select the waveform that we're going to use. I use a constant here because I have this waveform is basically the contents of the image that you just saw. But there are 2 waveforms together, concatenated after each other. So I use half of the length to select the second bank if I need to. Just some trickery. OK, so if we're not playing, then we're just silencing the sound. We don't do any computation because we don't need to. So that's the sequencer part. And everything below is that happens each sample, and it just generates this waveform and stuff. So we've got a bunch of envelopes. This is the oscillator. So it does linear interpolation over 2 values in the waveform. And it repeats around if it goes beyond the end of the waveform. Then these are some modulators. Something interesting here is I do each 33 samples I do this computation. I figured that I could get away with that, and it's not noticeable, so I could. And why did I do this here? Well, there's a power function, and this is computationally very intensive. And next to that, I am computing a polynomial here. A polynomial equation. And I've used Horner's rule to change this polynomial into a bunch of multiplication and additions. And this is also a very good performance improvement, because the multiplication and addition is a single CPU instruction, and the JIT can make really good use of this. So we got massive gains here, but it's a bit complex to explain this. But you know that sometimes you have to look at your equations and see if you can compute them with less steps, and that's good optimization too. Okay, so here we actually have the filter computations. These are a bunch of the same patterns you see. Like we do something with multiplication and addition of values in this filter bank, and it's a standard algorithm that happens for all of these filters. We add a constant here. This is also an optimization, which is a denormalization constant. And what this does is it adds a teeny bit of a number to the result. And this means that the number will never be something which is even smaller than that to 0. Because what happens is, at some point, if the number is low enough, then the IEEE floating point specification says that the floating point goes into a different kind of notation internally. And this notation is actually slower on CPUs. So we prevent that state from happening. And by doing that, we keep this computation very fast. I must say that this gets better over the years. So with advances in processor technology, this anti-denormalization doesn't really have much of an effect anymore. But it used to be a very big speed up, especially in like early days of software synthesizer development, especially when you were still doing that under DOS and arcade platforms and stuff. Okay, so these are a bunch of the same things. This is the TB filter. This is the diode ladder that I mentioned. It's a bit different structure, but still kind of the same. So it's mostly just the same. Here we multiply the output volume. And here we do the distortion, which checks if the value is high enough, then we flip it over. Not that complicated, but it looks complicated because I wrote it on one line for kicks. And the delay, so we put something in the ring buffer and we read something out of it and we wrap the position around, and that's it. And here we've got the load wave table. I think you like this one. So what we do here is we have the canvas. We create that using create element. We give it the width and the height that we get from the image, which is supplied using a new image on load. We get the 2D context and we draw the image into the canvas. Then we get the pixel data from this canvas back, and using some casting magic here, we initialize a float32 array with the pixel data from this context. So what happens here is first you need to get a uint8 array, because what you get back is from the canvas you get an array of 8-bit numbers. This is just a JavaScript array, so we convert it to a uint8 array first. And then what we can do is, using the WebGL typed array specification, we can freely cast this to another to another kind of typed array. And this means that this memory data just get mapped to this one. So we basically have about 1 million typecasts for free, because all we're doing is changing the surrounding object. So it's another optimization. I didn't need to cast this using a for loop. So okay, call back, and that's done. And the generating of the wavetable is here too. I won't cover that too much, but basically we're using a lookup table to speed things up. Then we're going to make this wavetable, and we're going to do some computations here, and then normalizing it. And that's it. That's the synth. 491 lines. So
I do have one more question.
Yeah.
All right.
I don't know how we're on time, by the way.
Nice. You gave an awesome demo, and I can imagine you play this thing all day long. But how do you check for regressions in your code?
With my ear. No, I kind of understand this code, and it's a very long and incremental process, you know. I mean, the nice thing about writing a synthesizer is that you immediately hear when something goes wrong. Each time you run it, you play it, you get music. And it's not like something will only happen in a very few cases, because the number of branches that you have in the main synthesizer logic code is actually very small, and that's with a purpose, because branches create computation overhead. So you want to remove those as much as possible.
So no tests?
No tests, no. But seriously, how are you going to test something?
Yeah, I was wondering, which is why I asked the question.
Yeah. Now, that's really a hard problem on its own, you know.
Just some selenium testing.
Well, yeah, you could do selenium testing, and you can make an image of the spectrum and compare that to a reference image. But yeah,
Cool.
That's crazy.
Thanks.
So, any more? I really could use a drink, by the way.
Let's do that then.
Okay, well, thanks, guys.